All right, let's work through an example for combined loading. This is, I'm calling example 4.22. And they want us to locate the point of highest bending stress and draw the representative volume element. So what is it that we have? We have a round bar over here that's been shaped into a form of a crank. Again, it's a round rod, which means it's solid. They give us the dimensions over here, and there's a single load right at the end. So they want us to calculate the point where we have highest bending, right? So if this was a regular like 2D problem, you might be thinking of doing like a shear moment diagram and figure out where the moment is biggest. This one we can do by inspection. We know that the formula for bending is 32 times m by pi d cubed. So in this formula, right, what could change over here to give us higher stresses? Well, the diameter could change, but in this case, it's constant 25, right? So this is constant. So the only other thing that would cause the bending to increase, right, would be a bigger m. So basically, we're looking for a high or the biggest moment. Now, there's a couple points where we would naturally be looking at. One could be this point over here. So I have 1,000 Newton force and it's 100 millimeters away. So it will cause a bending moment, right? Like so. And it would be of 100,000 Newton millimeters. And that's at this point. If we go at this other point, now this 1,000 Newton force is now 250 millimeters away. So it could create down like that, a 250,000 Newton millimeter moment. And if we look at this last one over here, well, the distance is going to be the highest, right? So we have, again, 1,000 Newton, but the distance is going to be 200 plus another 100 over here, or 300. And so this point over here would be the point where we would have the highest bending. Again, what is a moment? It's a force times the distance. So where's that moment going to be biggest? Well, where the distance is biggest because the force is constant. So I went ahead and already pre-drew this section over here. I'm imagining we're cutting right there. And we're going to figure out what's going on at that point. This problem doesn't give us any axis, but just to make our discussion more simple, I'm going to go ahead and add here an X, a Y, and a Z axis. And now we need to figure out the internal loading that is happening right at this cut. There's two ways to do it. The traditional way, which is where we section and we look at the front part and we solve for the reaction forces to make sure this is this is in equilibrium. Or there's a shortcut formula, or not formula, but the shortcut method, which is the one that I like to use. And it goes something like this. Basically, I'm going to look at my round or my bent rod over here, and I'm going to look at what forces are applying. In this case, I only have 1,000 Newton force going down. So I'm just going to go ahead and take this force, and now I'm going to put it right over here. So 1,000 newtons straight down. You can barely see that one. Now, basically another way to say this is I'm trying to figure out what is the resultant of this force at this point over here. Well, we know that the resultant force is going to be a force of the same magnitude and direction, but also that this force can generate some moments, right? So how do we know that? Well, we know that whenever we move a force anywhere that is not in its line of action. So in this case, if I slide this force up and down in this free body diagram, I don't have to worry about moments. But because I slid it over here, right, I went like maybe this way and then that way, I need to figure out what those moments are. So let's think about the moment about the X. So originally, right, this force is over here. It's at a distance of 250 Newton meters, right? So it would be creating at this point a moment of, so a little arrow like so. That moment is 1,000 newtons times 250 millimeters, or basically that equals to 250,000 Newton millimeters. And if we look at the direction, right, this would be in the x-axis, we look at the direction of this force, this is actually aligned with the axes of this round bar, right? So this is actually would be called not just a regular moment, but it's actually a torsion. Next, because this force is, we had to slide it some distance to get to the y-axis over here. How much was that distance? Well, it's this distance in the x. Right, so we can generate a force here, a moment here, about the y-axis of, this is going to be a bending moment of 1,000 newtons times the distance to get to the y-axis, right? Well, that distance is 200 plus 100 or 300 millimeters, which means I have a bending moment of 300,000 Newton millimeter. Now, usually you get some warning signs, some warning signs in your head, like boop, 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 this way too big number and this unit Newton millimeter for moments is kind of weird, but you'll see it's going to work out for us in this case. Okay, so at this moment, if you want to pause the video and actually section over here, maybe look at the front part, figure out those reaction forces to make sure that this front part is in equilibrium, and then you should be able to check that those forces and moments that you get over here are exactly the same magnitude as this one's, but they're going to be in the opposite direction. Alrighty, so let's assume you went ahead and did that. We want to calculate all the stresses, right? So specifically, we're looking for the bending, right? So where is the bending going to be the highest? Well, we have two moments, right? We already said this one's a torsion. So this one's actually trying to shear this shaft in this direction. And this one over here would be the bending moment, the one that would make it kind of flex like that. So we know whenever we have a bending moment like this being a circular cross section, right? This means we have the neutral axis right along or aligned with the y-axis, which means our points for the highest bending stress are going to be this top point and this bottom point over here. This is where the bending moment is going to be sigma b max, or the bending moment is going to be highest, top and bottom, right? What is the difference between the two? Well, let's look at this direction of this moment, right? It does something like this. So I like to draw it here on top, like so. So it's pulling on the top material, curving like this. And then at the bottom, it's compressing, right? So the top will be under tension. Let me put here maybe a T for tension. And the bottom one is going to put it under compression. So which one is the worst case scenario? Usually for a material, regardless of what is made up, usually the tension is worse than the compression. So if it's a metal, it doesn't really matter, but we'll just look at the top point for now. So we want to draw that volume representative element. So we'll draw something like so. Take a little cube here, kind of down like this, and in there. So let me draw it over here. And if we take this as, I'm going to call this point A. It's going to look something like this. So you don't have to, but I like to draw like this curvature of this rod over here. So it gives me a better sense of what is it that I'm looking at. So it looks more or less like this. That's that volume element. This would be our letter A, for example, if I were to call that point A. I also like to color the face of the cube, which I've exposed by cutting, right? So in this case, this is from cutting that bar or sectioning, this would be the face that I'm exposing. And that's very important because it means any forces applied, right, are going to be applied to that colored face. What do I mean by that? Well, if I have a bending moment like so, I already know that on top the material is going to be drawn, or it's going to be kind of be pulled, right? So that's the bending stress. This is a sigma b for bending. Again, it's 32 times n divided by pi d cubed. So let's go ahead and calculate that. So it's 32. The bending moment, right, for this one was 300,000 Newton times millimeter. Then divide this by pi times the diameter cube. Oops, let's put the value of the diameter. The diameter for the rod in this case is 25 millimeters cube. We can look at the units already, millimeters in the top and millimeters cube at the bottom. So we're going to cancel one of those. Whatever comes out of this formula is going to have units of newtons per millimeter squared, which is the same thing as a megapascal. So if we plug this in the calculator, here we go. Put it here. So 32 times 300,000, 1, 2, 3, divided by pi times the diameter, which is 25 cubed. And we get 95.56. I'm going to call this 195.6 megapascals. That's that bending stress that we have here. Sigma B. So we have a volume representative element, we have a stress. Are we done? And the answer is not quite, because we have other types of loading, right? We just took care of this one here, of this M that is causing the bending, but we have this 1000 Newton force, right? That is parallel to that cross section. So what is this force is going to create? I hope you remember that that's going to be a transverse shear. So if I draw this circle again, and if I color that 1000 Newton force coming down, we know that when we have a transverse shear on a circle, and this is the neutral axis, we know that the maximum for the transverse shear is going to be at these 2 points. That's the maximum, the tau max, right? What is that value? Well, from our equation book, we have our shortcut formula. It's 4V times divided by 3A. So this would be equal to 4V by 3A. And at the bottom, these tau equals 0. We cannot develop a transverse shear stress. So it means over here we got nothing going up and down, again because of transverse shear. But that's not the only thing we have, right? We also have this torsion up in front. So as I draw again this cross section, and maybe I should be coloring, so I'm drawing this one again so it looks a little bit nicer. We have this torque, right, and is wrapping around in this direction. So what does it mean? Right at this top point I have an arrow pointing like this. Right at this point I have an arrow down. Right over here the tangent is that way. Over here the tangent is that way. So the torque or the torsion is applicable at every single point. Right, we know the value from torsional stress. The tau is going to be 16T by pi d cubed. That's for a solid round bar. So let's look at our formula sheet. Bending stress, average transfer, torsion stress for solid round bar, 16T by pi d cubed. And actually, if you continue using the shortcut formulas for the round bar, you're going to end up memorizing, right? Because the bending is 32 times that bending moment, the shear is going to be 16, so about half the magnitude. Anyways, so let's go ahead and calculate this guy. So it's 16T. So 16 times the torque, which we said was 250,000 Newton times millimeter, divided by pi times 25, which is our diameter. This is in millimeters cube. So same thing, whatever comes out of this one is going to have units of megapascal. So let's go ahead and type that in the calculator. We have 16 times 250, 123,000 divided by pi times the diameter cube. And I get a value of 81.48. So we'll call it 81.5 megapascals. Right, this is the shear stress due to the torsion. So we have the value. Now, what is the direction of this arrow? On the top face is going here towards the right over here. So over here towards the right, which means on this guy, I have something going like that. And so this guy is the tau of 81.5 megapascals, right? This drawing is not complete. I need to complete it, right, by putting equal and opposite for the shear. So if the front one is like this, then the one here on this other side has to point towards it, which means this guy has to be opposite, and this guy has to be opposite. How do you know you have them? If we look at the two sides, they have to be opposite direction, right? Because at the end of the two, they have to balance. If they're pointing in the same direction, they're gonna push this element, like for example, up or down like that. We know it's an equilibrium. So once we have one, the one on the other side is opposite, right? If we look at these, just these two, they're gonna try to rotate the element, say counterclockwise, or in this fashion. So that's why we add these other two to put it back in equilibrium, same magnitude. So now we have these values for the tau. If we clean up this element a little bit more, what is it that we have? So I'm gonna look at just at the plane. So I'm gonna look at it from the top. I have this letter A, right? And then on this direction, I have my normals, which I previously calculated. These are the sigma bending, right? If we look at the direction of this arrow, right, straight perpendicular to this cross section, this is also the direction of the X. So we could also call that like a sigma X stress, right? And this is 195.6 megapascals. What else do we have? We have a shear, right? Remember, this is the phase where it's acting, which would put it right on this side over here. So what that means is I have a downward arrow here pointing down. So it means I need one like this, one pointing up, and one pointing this way. And if we pay attention to the axes over here, we're looking right at the top. The one that's going in this direction is the y-axis. So in this direction is the y-axis, which makes this stress a tau xy of 81.5 megapascals. How do I know it's a tau xy? Well, if I look at this arrow, for example, it's on the face of the cube that is, I guess, perpendicular to this x-axis. And the arrow is pointing towards what would be the y-axis. So this is a tau xy of 81.5. And so this over here would be the representative volume element. Well, this is the volume element. This is looking at just in 2D. And this is our answer. I want to remind you what I said on the lecture notes, that it's going to ask you for the signs. What do we mean by that? Well, we know the sigmas are trying to stretch that volume element. So this would be a positive stress over here, right? If it were negative, if it would be compressing the volume element, that's easy to see. The tau in this case, this is a positive because the arrows are pointing and they're on the X phase pointing towards a positive Y. So this would be a positive shear stress. However, for the formula, for the homework, I'm not necessarily asking for that. I'm just looking for this absolute value. So depending on how many types of different loads, you might have several of these loads combining, adding or subtracting the shear loads. So just report the magnitude or the absolute value and you would be okay. You don't have to worry about this direction yet, but you'll see next week that the direction is very important. Anyways, that's all I have for this one. Let me just double check. We have the volume element, we have the bending stresses, and we have the shear stresses from the torsional loading. Remember this 1000 Newton right at the top. It's a transverse shear stress, which means we don't have any shear loads, right? So always the transverse are going to be maximum right at the neutral axis and zero at the other ends. And that's it for this example.